This lecture is about the topic of torsion. It is chapter number 3 of the book of Mechanics of Material, 7th edition by Beer and Johnston. Before this topic, torsion, we have studied axial loading, stresses and strains under axial loading. We have studied about normal stresses and shear stresses under axial loading. Now we will study about stresses under torsion. So before that, we will discuss about how and where torsion or the torque is applied. There are some examples. For example, you can see an arrangement on your screen. There is a generator connected to a turbine. Whenever the turbine blades are rotating, they are applying torque on a shaft attached to it, and the shaft transmits that torque to the generator. Since generator has a weight and due to inertia it resists the rotation produced by the shaft, so the generator applies a reverse torque on the shaft, reverse to that applied by the turbine. So the shaft between generator and the turbine remains under two equal and opposite torques at the two ends. You can see at the end A, this torque is being applied by the turbine, and at the end B, a reverse or an opposite torque is being applied by the generator. So this shaft under two equal and opposite torques is actually twisting. It is about to twist, or it tends to twist between two opposite torques. This establishes the importance of the torque loading or the torsion. Now in this chapter specifically, we will discuss about what kind of stresses are produced due to the torque and what kind of strains are produced and how can we calculate the stresses and strains due to torque or torsion. Okay. If we move further, here's a body or a bar AB under torque or under torsion. Two equal and opposite torques are being applied at the two ends A and B. If we section the rod at C, at plane C, and see look at the internal forces, since the torque is produced by a force being applied at a distance or from the center point, if we assume or if we divide this cross-sectional area into small differential areas like this one, and let me call it a differential area dA, and a differential force dF is being applied on this area. Similarly, there are more differential areas and more differential forces being applied. Each force has each area has a distance of rho from the center. Remember that rho is a variable radius. If we look at the center, rho is equal to 0. And as soon as we go away from the center, the numerical value of rho radius will increase. So rho is a variable term being used for radius in this chapter. Okay. The torque is actually product of the force into its distance from the center about which it is producing torque or twist. So we can say there are multiple forces being applied at multiple areas. So we can say that torque is sum of the product of force and its distance from the center. Force into distance from the center is rho into dF. dF is force and rho is the radius actually, or distance from the center. This integral sign is used for summation. There are multiple forces and there will be multiple torques, and their sum is equal to total torque. Now we can convert force into, we can write force as a product of stress and area. So we can write this dF as a product of stress into area. Since F or dF is being applied parallel to the area here, dF is being applied parallel to the area dA. That is why we are calling it shear stress, tau. So here we have written force in terms of stress and area. We will use this expression of torque as equal to integral of rho into tau into differential area. Although the net torque due to shearing stresses is known, the distribution of stresses is not known. Okay, so we can find the net torque due to this shearing stresses tau, but we do not know the distribution of stress, where the stress will be maximum and where the stress will be minimum. The distribution of stress, shearing stresses is statically indeterminate, and we must consider shaft deformation. So we need to know the shaft deformation in order to calculate this indeterminate value of shear stress. Unlike the normal stress due to axial loads, the distribution of shearing stresses due to torsional loads cannot be assumed uniform. Okay, due to axial load, usually we consider normal stress as uniform, but actually it is not uniform. For example, there is an axial load P in our previous chapter. We studied that there will be a distribution of stresses. Stress will remain maximum in the immediate vicinity of the load, but it will be minimum away from the load. Here it will be maximum and here it will be minimum. But then we considered an average stress which is constant, average of maximum and minimum, which is equal to P over A. But in terms of shear stress due to torque, we cannot consider this distribution as constant. We must know the formula of maximum stress and minimum stress, and we must know their variation. So we will derive an expression for stress which will be a function of radius rho. Wherever we put the value of radius, whatever the value of radius is, we can find the value of shear stress. Okay. Now, here we can see that this shear stress exists on a surface which is perpendicular to the member axis. The axis of the member, which passes through the cross section, is perpendicular to this area where the shear stress is being applied. So the area perpendicular to member axis is under shear loading. This has been established now. Further, now if we see, if we take a small portion from the cylinder or from the rod, the shaft axis is perpendicular to this surface, and we have already established that the surfaces parallel to the shaft axis are under shear load. So this surface is under shear load. Similarly, the surface on the back of this surface, opposite to this surface, this one is also under shear. These two surfaces are perpendicular to the axis of the shaft. So they are under shear loading. Now, this shear force or shear stress and this shear force or shear stress, if we look at it from the top view, from the top, they are producing a counterclockwise rotation. This counterclockwise rotation must be balanced by a clockwise rotation in order to keep the equilibrium or to satisfy the equations of equilibrium. This means there must exist a clockwise rotation of same magnitude, which gives rise to another concept or another possibility, which is that the other two surfaces which are parallel to the axis of the shaft, this axis, they are under shear load as well. This shear stress or this shear load will be equal to the shear stress being applied on the other two surfaces. This shear stress will produce a clockwise rotation if we look at this element from the top. So this will balance out the previously known counterclockwise rotation. So it has been established that the surfaces of the element or the axial shaft which are parallel and perpendicular to the axis of the shaft are under shear stress or under shear loading. Another example of it is if we consider this structure. This is a shaft made up of axial slates, And we have marked some red color lines on this shaft, you can see here. And if we apply torque on the two ends and we twist it or rotate it, we apply a torsional load on it, so we can see the angle of these shafts has been, these slats have been changed. The slat slides with respect to each other when equal and opposite torques are being applied at the ends of the shaft. So you can see a change in angle of these slats. It means there is a shear strain here. Change in angle refers to shear strain, and definitely these slats are actually parallel to the member axis. So the slides parallel to the member axis and the slides perpendicular to the member axis are actually under shear loading. Okay. Now, after applying torsional loads, it is understood that the shafts are getting twisted. After twisting, for example, if here is a shaft and we have drawn a line AB on its outer surface, after applying a torque at the free end, we can see in the next figure that the point A, initial point A, has shifted to point A dash. So the line OA, line from center to the outer surface, has shifted to OA dash. There is a change in angle. This change in angle is denoted with phi, which is called angle of twist. This angle of twist is proportional to the applied torque and the length of the shaft. When subjected to torsion, every cross section of a circular shaft remains plane and undistorted. If we look at this diagram, it is a circular shaft. After applying torque, we can see that it is still circular. Cross section is still circular. It is planar and undistorted. Okay, but cross sections of hollow and solid circular shafts remain plane and undistorted because of a circular shaft is axisymmetric. So either solid circular shafts or hollow circular shafts will remain planar and undistorted because they are axisymmetric. But if we take an example of a non-axisymmetric body, for example a square or a rectangle, like in this figure, if we apply torque on it, the cross section is no longer the same. It is not planar and it is distorted one. So axisymmetry makes the structures to remain planar and undistorted after the application of torque. Okay, this is important for us. We will use it later. That angle of twist is proportional to torque and length of the shaft. Okay, now we will calculate shear strain. How can we calculate shear strain? Consider an interior section of the shaft. As a torsional load is applied, an element on the interior cylinder deforms into a rhombus. Here's the shaft. The external radius or the outer radius of the shaft is C, small c. The length of the shaft is L, and after applying a torque, we assume that there is an angle of twist equal to phi. If we take an internal surface of this shaft, in the next figure, you can see the outer dotted diagram is the total shaft, and we have taken an internal point inside, which is at a distance of rho from the center O. This radius rho is less than the total radius C. We will derive an expression in terms of general radius rho. On the outer surface, if there is you can see a red color element, a square element or rectangular element. After the application of torque, you can see this square or this rectangle has been transformed into a rhombus. The line AB initially, it has displaced, the point A has displaced from A to A dash. There is an angle of twist on the cross section, you can see angle phi, and there is another angle between initial line AB and the new line A dash B. This angle is gamma. Gamma is actually shear strain. So how can we calculate this shear strain actually? This arc A dash is common between the two triangles O A dash and B A dash. This arc A dash from this triangle can be calculated as A dash is common in the two triangles. It is same from this one. It is equal to rho phi. While from the other triangle, which is along the length of the shaft, it is equal to gamma L. A dash is equal to gamma L in this triangle. Okay, if we simplify it, so gamma will be equal to rho phi over L. Okay, gamma is a function of radius rho. Rho is a variable radius. If we keep rho equal to 0, it means we are at the center of the shaft. If rho is kept equal to 0, we are at the center and shear strain will be 0. It means center remains at its position even after twisting after rotation. And if rho is increased, shear strain will increase linearly, and at rho equal to its maximum value, which is C, gamma will be maximum. So gamma will be maximum if rho is equal to C. C phi over L is gamma maximum. If we compare these two expressions, first we find phi from here. Phi is equal to gamma L over rho, and we will put phi back into the expression of gamma maximum. So we can find that gamma is equal to rho over C gamma maximum. It means shear strain is a function of radius phi. Here C is maximum radius, which is a constant value. Maximum radius will definitely be a single value, it will be constant. And gamma maximum is maximum value of strain. Maximum is also a single value. So gamma maximum is constant, C is constant. So gamma depends upon radius rho. If radius rho is equal to 0, we are at the center of the circle. Gamma will be 0. If gamma is equal to, if rho is equal to 0, we are at the center. Gamma will be 0. If rho is equal to C, it means maximum radius. Gamma will be gamma maximum. So shear strain is maximum at the outer radius, at the outer surface of the shaft. Okay, moving further, this is how we can calculate shear strain from this expression or from this expression. Okay, if we want to find shear stress in the elastic region specifically, because for the elastic region we can use Hooke's law. Earlier we have derived this expression gamma is equal to rho over C into gamma maximum. If we multiply modulus of rigidity on both the sides, so gamma G, it is equal to shear stress. This is Hooke's law. So tau is equal to rho over C. Gamma maximum into G is tau maximum. So shear stress is also a function of radius rho. If radius is 0, if rho is equal to 0, shear stress will be 0. If rho is equal to C, shear stress will be maximum. And shear stress is a linear function of rho, linear function of radius. So at center where rho is 0, shear stress is 0. At radius C, outer radius where rho is equal to C, shear stress is maximum. And between 0 and maximum, it varies linearly. Similarly, For a hollow cylinder or hollow shaft, there are two radii, internal radius C1 and external radius or outer radius C2. So at radius C1, tau will be equal to C1 over C2 into tau maximum. C2 is outer radius, which is also called C. Okay, so here it will be minimum. At internal radius, stress will be minimum. At external radius, stress will be maximum. Below internal radius, below C1, inside the cylinder, there is no material. It is hollow. So if there is no material, there is no stress in this region. Minimum stress occurs at C1 and maximum occurs at C2. Okay. Now previously we have discussed that torque is equal to rho stress into dA. Integral of rho stress into dA. Probably in the second slide or third slide of this lecture. Okay. Now we can put expression of tau from here to here. It will be integral of rho to rho over C tau maximum into dA. Or it will become tau maximum is constant, C is constant, it will be rho square dA. Rho square, integral of rho square dA, this term is equal to polar moment of inertia, J, capital J. Polar moment of inertia or J is actually resistance to torsional loads. It is resistance to twisting. It is a similar quantity as the second moment of area or moment of inertia, I, which is resistance to bending, and J is resistance to twist or resistance to torsion. J for solid cylinders is equal to pi by 2 radius power 4, C is radius, and for hollow cylinders it is pi by 2 outer radius power 4 minus inner radius power 4. So we can simplify it as tau maximum over C into J, or we can write tau maximum as T C over J. This is a very famous expression and we will keep on using this expression throughout the chapter. For maximum stress, this expression can be used. Maximum stress is equal to torque into outer radius divided by J, and J can be found from the given expressions for cylinder, solid cylinder and hollow cylinder. And if we write a general value of tau, it will be T rho over J. We will replace the maximum radius, outer radius, with the general radius rho for general expression of tau. So if we have a hollow cylinder, it will be tau minimum or tau 1 divided by tau 2 is equal to C1 over C2. Or at external surface, it is tau maximum is equal to TC1 to TC2 over J, and internal radius it is tau minimum equal to TC1 over J. We can use either these two expressions or this expression. Okay, so this has been established to use this expression of tau maximum throughout the chapter, TC over J. Moving further, now we have established that if a surface of a shaft element is parallel or perpendicular to the member axis or shaft axis, like element A, the two surfaces of this element are either parallel, this one is parallel and this is perpendicular to the member axis. So this member or this element is under pure shear loading and the shear stress will be maximum, tau maximum at outer surface. But for any other element, for example, element B, if it is not, if the sides are neither parallel and are not perpendicular to the member axis, so they may be under either normal stress or both combination of normal and shear stresses. So first, we assume a special case. I will intersect this element at a diagonal, and these angles are definitely 45 degree. I will draw it here separately. 45 degree, this one or this one. If we intersect it like this or like this, depends upon us. So if I assume this surface, the surface which we have separated or we have sectioned will be under a reaction force which is perpendicular, normal force F dash. Now in order to find F dash, we have to resolve other forces into their components. These forces, this stress tau maximum can be converted into force if we multiply it with this area. This area is A naught. This area is A naught. This area is A, and A is equal to, by Pythagoras theorem, it is equal to square of A naught plus square of A naught whole square root. It becomes square root of 2 A naught. So A is equal to square root of 2 A naught. Okay. Now in order to find this force F, we can divide these forces into their components. One component in the direction of the force and the other component perpendicular to it. These components which are in the direction of the force, this angle is definitely 45 degree. This component is tau maximum A naught cosine of 45 degree. This component is also tau maximum A naught cosine of 45 degree. So if we take summation of forces equal to 0 in the direction of F, there are three forces. One is force F dash or F, and the other two forces are tau maximum A naught cos 45, tau maximum A naught cos 45. The summation of forces, force F dash and the forces tau maximum A naught cos 45 are in opposite direction, so we can take opposite signs with them or take on them on the opposite sides of the equation. So F is equal to 2 times, there are two forces, tau maximum equal to tau maximum A naught cos 45. Okay. Cosine of 45 is equal to 1 over 2. So it can be further simplified as F equal to tau maximum A naught square root of 2. This is a normal force on area A. So if we want to find normal stress, sigma 45 degree. Sigma at an element at 45 degree will be equal to force divided by area. Normal stress is force divided by area. Force is tau maximum A naught square root of 2, and area A has already been calculated, which is equal to square root of 2 A naught. So we can cancel out A naught and square root of 2 with square root of 2. So sigma at 45 degree becomes equal to tau maximum, and we know that tau maximum is already Tc over J. If this sigma is compressive or tensile, if it is tensile like this force, it will be positive. If it is compressive, it will be negative, but the magnitude will remain the same. It can be, sigma can be either positive or negative. So now we have established that if the two sides of an element like element A are parallel and perpendicular to the member axis, this element is under pure shear stress will be maximum, and maximum shear stress is equal to Tc over J. If an element is at 45 degree with the member axis, if this angle is 45 degree, the element is under pure normal loading. Normal stress at angle 45 degree will be Tc over J. It will be positive on the two of the on one plane, and it will be negative or compressive on the other plane. Okay. So torque may produce shear loading, pure shear loading, or pure normal loading, or it can produce a combination of normal and shear loading if the angle is neither 45 degree nor 0 degree and nor 90 degree. Okay, so we have just in this course we have just studied about we will study about two special cases, pure shear loading and pure normal loading only. Both are equal to Tc over J. Now we have established that at 45 degree elements, the elements at 45 degree with the member axis are under pure normal loading, which will be maximum normal stress, and the elements parallel or perpendicular to the member axis are under pure shear loading. So now we can see, we already know that ductile materials generally fail in shear, while brittle materials are weaker in tension rather than shear. So if we apply torque on a ductile material, it will fail due to shear because it is weaker against shear loading. So if it fails due to shear, it will fail on a surface, or it will make a surface which is perpendicular to the member axis, this axis, because the surfaces perpendicular to the member axis are under maximum shear. Similarly, brittle materials which are weaker under tension or normal stress, they will fail like this. This angle will probably be 45 degree because normal stress is 45 is maximum at 45 degree if the loading is torsion. Remember that this kind of failure is under torque or torsion load only. You can observe this in your general observation in your real life and the objects around you. Okay, this is enough, and now we will move towards a sample problem or an example problem. Sample problem number 3.1 from the textbook. Okay. Shaft BC is hollow with inner and outer diameters of 90 mm and 120 mm. We have three shafts given in this diagram: shaft AB, shaft BC, and shaft CD. Remember that A, B, C, and D are pulleys, and between each two pulleys there is a shaft. The pulleys are under torque. Torque on each pulley is given to us. Diameter of each shaft is either given or required. Length of each shaft is given. Material is given. So among these shafts, the center shaft, shaft BC, is hollow from inside. The inner diameter and outer diameters have been given, 90 mm and 120 mm respectively. Shaft AB and shaft CD are solid of diameter D. So the outer two shafts, this shaft and this shaft, they are solid and their diameter is D, which is unknown. For loading shown, determine in part A the minimum and maximum shearing stresses in shaft BC. So in the center shaft, we have to find minimum and maximum shearing stresses. Since it is a hollow shaft, so for hollow shaft, minimum shear stress is at internal radius and maximum shear stress is at external radius. Okay. In part B, we have to determine the required diameter D of the shaft AB and CD if the allowable shearing stresses in these shafts is 65 megapascal. So in this part, allowable shear means term maximum is given. Allowable is already maximum, always maximum. It is given, and we have to find diameter. So we can find radius actually. From radius we can find diameter. So in the first part, we have to find term maximum. In the first part, we have to find tau maximum and tau minimum in shaft BC. And in the second part, we have to find diameter of the shaft AB or CD, which is same for AB and CD. Okay, to find shear stress or to find diameter, we can use this expression tau maximum is equal to TC over J. So we need torque and radius to find maximum shear stress. J can also be found from radius. J is equal to pi by 2 radius power 4. So we need radius and torque. Or if we want to find radius, we need torque and stress. So in the first part, we need to find stress. So we need radius and torque. Radii, internal and external radii of the shaft, center shaft BC are given. First, we need to find torque in shaft BC. Similarly, for part B, we need torque in shaft AB. So torques in the pulleys are given. We have to find them shafts in the. We need to find torques in the shafts. So we have to section this member between point A B to find torque in shaft AB. Similarly, section between point C D to find torque in shaft BC. Similarly, between C and D to find torque in shaft CD. So we'll start from one end, from end A. We have started from end A and we have sectioned the shaft AB. At end A, there is a applied torque 6 kilonewton meter, which is given in the problem. And at the point of section, there is a reaction torque TAB, which is unknown. By keeping summation of torques equal to 0 using equation of equilibrium, these two torques are in opposite direction. So TAB minus 6 kilonewton meter is equal to 0. So TAB is equal to 6 kilonewton meter. TCD is also the same. It is from the other end. We do not need TCD actually. TAB is enough for us. Similarly, if we section the shafts between B and C and we draw it from one end, from end A. So at end A we have an applied torque of 6 kilonewton meter. At pulley B, it is given in the problem statement TB is 14 kilonewton meter. Here is a unknown torque at the point of section TBC. So if we keep summation of torques is equal to 0. So 6 kilonewton meter plus 14 kilonewton meter minus TBC, because TBC is in the opposite direction to 6 and 14 kilonewton meter torques. So TBC comes out to be 20 kilonewton meter. So now we know torques in shaft BC and shaft AB. Okay, we will move towards the solution of our problem. In part A, we were asked to find maximum and minimum stresses in shaft BC. Okay, shaft BC is a hollow shaft. Internal and external diameters were given. Internal diameter was 90 mm, so internal radius is 45 mm. External diameter was 120 mm, so radius is 60 mm. In terms of meters, it is 0.045 meter and 0.06 meters. Okay, we can find J. J is pi by 2, outer radius power 4 minus inner radius power 4. For hollow shaft, it is like this. So by keeping the values of radii which are given to us, we can find J in terms of meter power 4, which is 13.92 into 10 power minus 6. It is established that stress will be maximum at outer radius. So tau maximum is at outer radius C2. Torque in BC into C2 divided by J. Tau maximum is equal to TC over J. T in shaft BC. C is outer radius. Here it is C2 and J has been calculated already. So tau maximum is actually tau 2 at outer radius C2. It has been calculated as 86.2 megapascal. Tau minimum will be TBC C1 over J, or we can write the same expression, tau minimum or tau maximum is equal to C1 over C2. C1 and C2 are known. Tau maximum has been calculated already. So we can find tau minimum, which is equal to 64.7 megapascal. Part A has been solved. We were asked to find maximum and minimum shearing stresses. In part B, we were asked to find diameter of the rod or the shaft AB. We will find radius of the shaft AB, then we can find diameter. So radius can be calculated from the same expression. Tau maximum is equal to TC over J. For shaft AB, we have to find diameter of shaft AB. We will find radius first. So we can use TAB C over J. For solid shaft, J is pi by 2 C power 4. This C and this C can be cancelled. Here will be C power 3. It will be like this. Tau maximum is given in part number 2, it is 65 megapascal. TAB has already been calculated on the previous slide, it is 6 kilonewton meter. You can write this 6 as 6 into 10 power 3 kilonewton. Okay, so C becomes 38.9 into 10 power minus 3 meters. This is radius. So we can calculate diameter from the radius. Diameter is 2 times radius. And 10 power minus 3 meter is equal to millimeters. So diameter becomes 77.8 millimeters. I hope it is very easy. Either we can find radius or we can find maximum stress if we know torque in each shaft. Okay. Moving further, the next topic is angle of twist in elastic range. We have found expressions for shear strain and shear stress. Now we will derive a small expression for angle of twist. What is angle of twist? Here phi is angle of twist. After applying torque, the point A has been moved to A dash and it is making an angle at the center, which is angle of twist. Previously, we have already discussed that gamma maximum or maximum shear strain is equal to C phi over L. C is outer radius, phi is angle of twist, L is length. We also know that shear strain is equal to shear stress divided by G. This is Hooke's law. So gamma maximum is equal to tau maximum over G. Tau maximum has been derived as TC over J. This G is on its place. These two expressions, this expression and this expression, have the same left hand side. So we can equate the right sides of these two expressions. If we equate the right sides of the two expressions, we can find we can find expression for phi. C phi over L is equal to TC over JG. So C and C are cancelled. Phi becomes TL over JG. This is angle of twist or deformation. This expression is similar to the expression of deformation which we have derived in our chapter number 2, which was linear deformation is equal to PL over AE. In these two expressions, if we compare torque T and load P, they both are loads. Length L and L is common. J in the first expression is geometry. Here A is geometry. Here G is material property. Here E is material property. So they are similar kind of expressions. Previously we know that if we want to find deformation in a structure which has a variable area or loads are being changed, so we can find total deformation is sum of the individual deformations. Similarly here, if area is being changed or if material is being changed or if loading torque is being changed, we can see here between A and C we can section this, between C and D we can section it, between D and E we can section it, between B and E we can section it and find torques. So similarly we can find angle of twist in each of the shaft or in each of the portion, and then we can add it up. If the angle of twist or if the torque in each shaft in the same direction, clockwise or counterclockwise, we can add up all the angle of twists. If in any section the torque is in opposite direction, we will subtract that angle of twist from the total. So total angle of twist will be sum of individual angles of twists. We will use this expression in our numerical problems to find angle of twist. I have chosen some numerical problems from the exercise of this chapter. which we will discuss in a separate lecture. This lecture or this chapter, the theory part of this chapter has ended at this topic. It is enough for our course at undergraduate level. So from the next slide onward, I have chosen some numerical problems from the exercise 3.5, 3.15, 3.25, 3.35 and 3.38. The last two 3.38 and 3.35 are on the topic of angle of twist. So I will upload a separate lecture on solution of numerical problems from the exercise. I hope this lecture is enough for you to understand basic concepts of torsion and the stresses in a member or in a shaft under torsion, the normal stresses and the shear stresses. So if there is anything to discuss, if there is any query, you can send me an email and I will try to answer your questions. Thank you very much.